Okay, so today is the first real lecture, and it's kind of my propaganda speech to talk you into sticking with this course. It's basically a motivation why spatial data science is important, and then a little bit of jargon. You know, anytime if you have no geography or GIS background, some of this terminology may seem a little strange, but it's just terminology. So once we're all on the same page, then we can move on with the actual techniques. And I also populated the chalk site with like 6 weeks ahead of time, so you can take a look. If you have issues accessing some of the materials, let us know. I know that some of the guest people can't see everything, and you know, as I told you, I'm not that familiar with chalk, so we'll figure out how to set it up. So what we're going to do this afternoon is start with some motivation. Why is spatial thinking, from my perspective, all of a sudden the thing to do in social sciences? Then give you some, as I said, some definitions about what we mean by spatial analysis, what it consists of. Spatial data science, which is the latest buzzword, which is basically the same thing, but with a little bit more computer science thrown in. And then we switch to more methodology, and I'll go over different types of spatial data and what that means for the types of research questions we can address. You could, of course, flip that around and start with the research questions and then see what data can be used for that, but I just find it a little easier to start with the data structures and then move from there. And then I'll end with some classic pitfalls. These are the type of things that your discussant, when you present a paper, will come at you with if you present this. And I just want you to be aware of this, and we'll revisit this as we go on in different contexts. Okay, so what's the big deal? Why do we now look at the spatial context in the social sciences? And there are basically 2 dimensions from which we can approach this. One is a substantive dimension, which is, of course, the more interesting one from a theoretical point of view. But there's also a very practical one, which is more data-driven. And so from a substantive point of view, the main change in thinking in a lot of the social sciences is a switch from the individual decision-making person making individual decisions, you know, maximizing utility and all that great stuff, towards taking into account the interaction between that individual and its surrounding context. You know, peer effects, how you get influenced by others, how others adopt what you are doing, the fusion of thoughts, of innovation, of techniques, of political ideas. How do the social networks that exist represent themselves spatially or geographically, and vice versa? Do geographic networks have a social network counterpart? Very important in economics, spatial externalities, the fact that the activities at one location affect the profits or the costs of activities at other locations, and how do you take that into account? A very important concept in that respect is this concept of a spatial multiplier, which basically means that if you carry out a policy or an intervention in one particular location, that its effects carry over beyond that location. So let's say if you do a crime intervention in one particular neighborhood, it not only affects that neighborhood, but also the surrounding neighborhoods. And so that's an important concept that we will try to quantify in the sense of how far does this go and how strong is it. Then we have other motivations. Those of you in sociology may be familiar with Andy Abbott's paper on time and space. Is basically a review of the Chicago school way of thinking about space and time. And his quote is that all social facts are located, and so located in geographical space. And we have different aspects of this. We have spatial mismatch. For example, when people don't live where they work, and in a lot of poverty analysis, that's a very important aspect, that people just cannot get to work because there is no infrastructure to get them there. Spatial disparities, nothing is uniform across space. Some areas are better off than other areas, and that is not random. And that's a concept that we'll revisit in a couple of weeks, the concept of spatial randomness. And we're, of course, interested in situations where it is not spatially random. And so there is structure. We try to discover that structure. We try to understand that structure and explain it. And that's what we're going to do. Neighborhood effects. A lot of recent work looks at the effect of the context, the neighborhood. This is called contextual effects in some literatures. Basically, how does what happens around you affect you, and how do you in turn affect what happens around you? And we'll look at that in more detail later. So as I mentioned, a first dimension of the motivation is substantive, actually understanding phenomena. The other dimension is more practical, and it's the data. And there's been a major change over the years. When I started working in this area, very few data had the locational context with it. Now just about everything has. So we have a lot of what we call geolocated observations. For example, street addresses of crimes, social media data where the GPS in the smartphone tells you where the message was tweeted or when the posting was made. Sensor data like the array of things that we'll talk about in a second. These are all specified with a particular location and often also a timestamp. Another motivation for doing spatial data analysis is that very often, and in fact this is the rule rather than the exception, the cookie cutter, so to speak, the scale at which we measure social phenomena tends to be administrative units. And they almost never match the spatial imprint, the spatial scale of the processes that we're actually studying. For example, census tracts are often used as proxies for the concept of a neighborhood. Well, census tracts are not neighborhoods. I bet you very few of you actually know what census tract you live in, but you do know what neighborhood you live in. And so this is a problem with housing studies, this is a problem with crime studies, this is a problem with health studies, in that the container in which the data are measured does not match the process. And so as a result of that, some of the information about the process will be included in neighboring containers, and that's where the spatial comes in, the spatial spillovers come in. So the mismatch, then a little more technical, error terms, the precision of measurement may have a geographic imprint. And for example, in economics, in the analysis of real estate or house prices, there's such a thing called a hedonic model. A hedonic model explains the price by the characteristic of the good that is being sold. So for a house, the price of a house is explained by the characteristics of the house. How many bedrooms, how many bathrooms, garage, fireplaces, all that stuff, right? Now, one very important aspect of the draw of a particular home is what happens around it. But that's not included in these individual characteristics. So that is another way in which spatial effects come into the picture. And then, again, as I said, this is a little more technical. In the sensor world, the precision is very high right where the sensor is. But as you move away from the sensor, the precision gets worse. And again, this isn't random. This is structured in space. As you get further away, things get worse. And we'll see this concept over and over, this concept of distance decay. There is a connection between the distance of separation and the correlation or the error term or these other things that we'll make more concrete later on. And then finally, the most technical of them all is what is called in the literature the change of support problem. Now, support is a statistical term. Support means the range of data that you actually observe. So say if you do a survey of households, and their incomes are between, let's say, $5,000 and $30,000 a year, that is the support. That is the statistical support for the variable income. So you, in other words, you don't know anything about anybody who makes 100,000 because they're not in the support, right? Now think of this spatially. In space, the support will be the area in which you have your measurement. And for a lot of studies, for a lot of analyses, the information that you have does not pertain to the same area. For example, if you do educational studies, you may have information on school districts. School districts do not match census tracts. So you have information on the socioeconomic characteristics of the quote-unquote neighborhood as the census tract, and then you have other characteristics of the school district. How do you get these to match? That's an inherently spatial problem that will require spatial analysis. So just some examples, classic examples. These are the readings that you might want to look at as not critical, but if you're interested in this area and if you have time, I would definitely recommend reading this Of Time and Space article, especially if you're a sociology person. This really puts things into context. And if you read between the lines, you will sense that this is written a while ago, but you will sense that at that time, this was not an automatically accepted thing. Taking space into account was considered weird. And I've been there. I started in this world, and basically it was not accepted to do that in proper social science research. This has completely changed. And some of the reasons why it's changed are spelled out in this article. There's a whole initiative that I was involved with, Spatially Integrated Social Science. There's a whole book about it, but this article gives you some motivation. It was based on the proposal that we wrote to National Science Foundation. John Logan has a nice piece on spatial thinking in the social sciences, which is a little more recent perspective compared to the Abbott piece. There's a recent piece in Science that is it's only a page and a half. It basically is a statement by CDC and NIH as to why they are now taking spatial aspects into account in their research, in their analysis, in their funding, which is a total turnaround. And then finally, you may be aware of this, in the beginning of the Obama administration, there was a circular at OMB which promoted effective place-based policies. So again, location, place, space were brought explicitly in the policy analysis, and it's a nice little piece for perspective. Okay, so now we know why we're doing this. What is it that we're doing, right? What is spatial analysis? And one thing that I want to point out is there's nothing new here. You may be familiar with this map. This map is in every textbook of GIS or spatial analysis or spatial statistics, but actually it's not right. There was no spatial analysis here. This was a totally different approach into finding the patterns. There's a very interesting book, and every time I do this lecture, I forget the title of it. But yeah, something with ghost. But it's fascinating. It's fascinating because it actually tells the story of Dr. Snow and how he actually put two and two together and figured out that the people who drank water from that particular pump were the ones who got the cholera. And ghost map, yeah. So it's nothing to do with spatial analysis. But of course, it's a nice, this is real spatial analysis. It's, 2 years ago, but it's the same now. This, the Chicago Trib does this. It puts out maps of the crimes. And so then the question is, this is a map, but it's more than a map. What is really going on here? Are there any patterns in here that are interesting? Can we identify them? Can we find the clusters or the hot spots or the cold spots? And then can we explain them? Can we figure out why these places are different than other places? So that's really what we're going to be doing, right? I can't say this enough. Spatial analysis is going beyond mapping, okay? All too often, the general impression is that GIS and spatial analysis is about making a map. The map is only part of the story. In fact, the map is really secondary to the story. It's really about learning from the data and providing what is called added value. So it's every imaginable manipulation of geographical spatial data that you apply to gain knowledge. And so spatial analysis you can think of as being part of this, this actually comes out of computer science, this idea of knowledge discovery. KDD is knowledge discovery from data bases. It came from the computer science database literature, but they have this kind of cute little sentence, you know, from data to information to knowledge to wisdom. So you don't just stop at the information part, you just keep pushing it. And the idea is that we really want to squeeze information out of the data that changes the way we think about things. That's the ultimate goal, right? So what do we do? What are the kind of questions that we ask? And I purposely put this way. This isn't very sophisticated, but this kind of gets it across at what it is that we're actually doing. So where are things happening? Okay, so we have to figure out locations, patterns, clusters, hotspots, disparities in space. This is where a lot of the mapping comes in, but it's mapping plus. It's mapping plus exploration, exploratory data analysis, as we'll see later. Then much trickier, why do things happen where they happen? So what are the location decisions? How we can start understanding this. Then the third one is about context. How does what happens in one particular location affect what happens around it and vice versa? So there's this feedback effect. And by the way, parenthetically, it is this feedback effect, this interaction, that makes spatial analysis difficult. In a time series, the past predicts the future. The future doesn't predict the past. In space, it goes both ways. As I often say, I am my neighbor's neighbor. So if I influence my neighbor, then my neighbor influences me. So I influence myself through my neighbor. And it's this constant feedback, this simultaneity, that we have to keep in mind when we do spatial analysis. This is something that you don't have to think about when you have the traditional, you know, independent, identically distributed data points. They're all independent, they don't influence each other. In time series, there is influence, but it's one directional. In space, it's two directional. It's not just two-dimensional, it's also two-directional. So it comes back at you. And then a fourth aspect, which is very important for practice and policy, is the whole optimization idea. You know, given the age distribution in a city, how many schools do we need and where should they be, right? This big deal in Chicago after the school closings, how did that affect the layout of the city spatially? You know, so there's a whole branch of spatial optimization that looks at these kinds of questions. So for those of you who are not used to a geographical or a spatial perspective, I have this little example here to kind of try to get it across. One is analysis spatial and one is it not spatial, right? And the critical difference is that where you observe phenomena matters. Where the activities happen matters. When location matters, then we have a need for spatial analysis. When location does not matter, spatial analysis is not going to help you, okay? So more technically, it has to do with information content. What you learn from the data. And if the location changes and your information content changes, then that's where spatial analysis is relevant. And the example I use is actually a real example. There's a fake city here and a real city here, and it's Milwaukee. And many of you might know that Milwaukee is one of the most segregated cities in the US. And this is a map of census tracts in Milwaukee that gives the percentage African American, right? One of these maps is the real map. The other map is a fake map where we take the same data So let's say we have 100 census tracts with 100 numbers. We take the same 100 numbers and we randomly put them into space. This is the fake map. The one on the right is the real map. And it's real, it's very segregated. All the browns and reds are together, all the blues are together, right? This is the same data but switched around. So obviously, this is an example where location matters. But very interestingly, and it takes a little while to get this subtlety, the non-spatial analysis is not affected. So this is a histogram with the distribution of percent African American by census tract for each of the two maps. Now, why is it identical? Because the histogram doesn't know where those observations are. There's no location here. So this is an example of non-spatial analysis. You can't tell the difference. Now, one of the things we're going to learn is measuring spatial autocorrelation. And one of the tools we're going to use is called the Moran scatter plot. And here we do see the difference. The one on the right has a very positive, steep slope, a very high degree of positive spatial autocorrelation, which means nearby things are very similar. Remember the map, all the reds together, all the blues together. This is about as flat and spatially random as it can get, a slope of 0. That's our fake map. And it is like this because we constructed it like that. We randomly reshuffled the data points over the map, and that is a technique that we'll use again and again later on to carry out statistical inference. So this is an example of where the spatial analysis matters. And so what are the kinds of things that we're going to be doing then? We're going to start very simple, and I may have mentioned this last week, but one of the ideas behind this course is to go through a progression of increasingly more sophisticated and more technical spatial analysis. So we start very simply with visualizing data, making maps that show interesting patterns. And this is not just a random thing. I mean, this won't be a cartography course, but there are some principles to keep in mind. And you can make good maps and you can make lousy maps. And I've seen a lot of lousy maps made by taking the default in a not-to-be-named statistical package. So then we move on to exploratory spatial data analysis, which is actually interacting with the data to discover interesting patterns. And then we get at the last point where we do the actual modeling. So we try to explain the patterns. We specify mathematical equations for regression models. We estimate them, carry out specification tests, and then maybe use these models in an optimization or a simulation or a prediction context. And so that's the whole range. In this class, we won't deal with the modeling. We kind of stop here. In the spring class, we deal with the modeling exclusively. Okay, so that's spatial analysis. Now what is spatial data science, right? It's a buzzword. Nobody knows what it is. It comes out of this whole big data phenomenon, right? And my definition of big data is you know it when you see it, right? This is a very practical definition because typically data is big when you cannot handle it with what you have. And what you have varies, right? You cannot handle it with the current X. And what is X? Your hardware. You have a tiny laptop, 100,000 data points, you don't have enough memory, forget it, right? Memory, same thing. I mean, you may have 2 gigabytes, I may have 32 gigabytes. I can do bigger data than you, right? So what I call little data, you call big data. The software. Some software doesn't scale very well to very large data sets. Some people call big data whatever doesn't fit in an Excel spreadsheet. I mean, it's all over the map, right? One kind of consensus is this. It used to be the 4V, now it's the 5V, you know, volume, obviously, velocity, the speed at which the data come at you. A lot of these new data sources are near continuous. You know, that used to be the case only with the stock market, but now all kinds of stuff is measured in almost instantaneously. variety. A lot of these data are unstructured. The value is obviously the economic interest, you know, the reason why companies like Google and Facebook exist and make a lot of money. And then veracity is a little more controversial. You know, there's a whole discussion as to what you can actually do with this big data, and we might talk about that or we might not. If you haven't seen this book, I highly recommend it. It's written by somebody who works for The Economist. It looks at a number of aspects of big data. It's a couple of years old, but it's still highly relevant. If you have time and you don't know what to do, I would recommend it. So what are some of these issues related to big data and analysis? A first very important issue is, what is the sample size? Do you actually have the population, so the whole notion of a sample is irrelevant? Or do you have one observation, which is, again, not what we're used to. Just think about this for a second. It's not, you have all the Twitter posting, everything, right? Is that the population, or is that just one snapshot of what's going on? The argument is that the size of the data compensates for everything else you've been taught to do, like being precise in your measurement, thinking about your sampling framework, avoiding systematic measurement error, etc., etc. If you read some of the columns, or the early columns about big data, the end of whatever it was, not the end of science, the end of, it was not really, the end of modeling, I think it was. You don't need to, the end of theory, yes. The end of theory in Wired magazine. Very controversial statement. Is it or not really, right? And one of the things with big data is that the emphasis shifts from the classical, you know, social theory causation framework. You know, if you're in economics, everything is about causal effect. What is causal, what is not causal? In sociology, same thing. You know, when can you say that A causes B versus just being correlated with B? And so A happens to happen at the same time as B, but does that mean that A really makes B happen? That's very difficult to say. And the one way of thinking about big data is just forgetting about that whole thing. You don't really care. All you care is, can I predict how many people are going to be on the next flight between San Francisco and New York? And you don't really care whether, you know, the number of seats in some hotel causes that, as long as you can use that variable to predict the number of flights. And a lot of machine learning in a big data world is about correlation. Can you discover patterns, sometimes highly nonlinear patterns? You know, the big deal right now is deep learning. You know, deep learning is in essence fitting a highly nonlinear model, and you can fit it because you have the hardware to fit it. You can't do that on your laptop, right? You just throw tons of computing power at it, and then you can actually get all these nuances out there. But again, a neural net doesn't explain anything. It's very good at prediction. In fact, oftentimes it's hard to beat, but nobody really can figure out what is happening in the box. You know, what are the relationships that get us to get this good prediction? And that's, from a theoretical point of view, from a social science theory point of view, that's a main drawback. Because if you're trying to predict stock prices, you don't care, as long as you make money, right? If you're trying to understand how the world works, it's a different story. So that's something to keep in mind. In terms of the social sciences, my take is that the major change, the major new thing, so to speak, is not so much the big data part, but the new data part. These are data that in my days just didn't exist, right? You have these sensors, the whole smart city movement. You have open data portals. We'll use an open data portal in the lab where a lot of administrative data are made public, and a lot of that is geocoded, is geographically defined. I believe the Chicago Open Data Portal now has over 1,000 data sets in it. And New York City has a big open data portal, San Francisco. I mean, they all look the same because they all use the same software. Most of them use Socrata as the software that drives the portal. So if you've seen one, you've seen them all. They all look the same, so it's easy to move from one city to another. The whole social media data, that's a very recent phenomenon. And much of this, not all of it, but much of this is geocoded. And if it's not geocoded, very often there's enough information in the message or in the picture that you can actually figure out where it was posted. So there's a whole technical area of figuring that out, inferring location from the contents of the message or the contents of the picture and so on. 311 calls. These are, a gold mine for all kinds of different events that happen. People calling about cars being parked in their driveway, about potholes, about lights not working, and so on. So a recent paper, I think it just came out, looks at neighborhood transitions in New York City based on 311 calls about obnoxious things. So you have this whole ethnic transitions in neighborhoods in New York City, and these people use 311 calls to find borders, fuzzy borders, between areas of transition. And then cell phone data. If you can get them, they're also a gold mine because they're geolocated. Your cell phone knows where you are, and they're time-stamped as well. So just to give you some concrete, this is the array of things that's done here at the Computation Institute. There's about, I think the initial phase is about 500 of these sensors will be put all over Chicago. They look like this, and they measure just about anything you want to measure, but obviously there are some constraints on this. But they measure air quality, temperature, movement of people, things like that. It's actually very interesting with high potential. This is the way the City of Chicago Open Data Portal looks. If you haven't checked it out, I really encourage you to do so. In fact, you're going to have to in the lab and for the assignment. But it's a gold mine, but don't think for a second that you just have to click on this and get going with your analysis. I've picked an example for the lab next Monday that will show you several of the, as I mentioned last time, gotchas that you have to be really aware and wary of before you do any analysis. This is not clean data by any, in any sense. This is an example of the use of cell phone data out of the Sensible Cities lab at MIT, where they had information on calls by location and follow the flow of the people based on the phone call. So you may be familiar with there's a very famous animation from the Sensible Cities lab that show during the European Soccer Championships, Italy scored a goal. You can literally see it on the map because everybody calls their friend and says, "Did you see that?" And then it kind of comes up. So there's other more relevant applications. This is some work I've done with Sarah Williams on Foursquare and Twitter locations and the concept of digital neighborhoods, and we'll maybe talk about that more in detail later. So where does this fit into the bigger picture, right? There's some new analytical paradigms. I mean, you see here there's a new program, a master's in computational social science. Where does that come from? That comes from the appreciation that computation has become, because of the cheap hardware that we now have, as a very valuable way of carrying out scientific discovery. In fact, it's argued as the third approach. I think the first one is theory and the second one is experimentation. So that has led to this idea of computational social science. The software companies, the big companies, Facebook, Microsoft, and so on, go even further and talk about data-driven research. So this is where this concept of no more theory or theory is irrelevant comes from. Everything is from this big amount of data, which is not just to make money, because that's always been the case. People have always figured out how to use data to make money, but also to learn about the world, to promote social science in particular. And so that's often referred to as the fourth paradigm. So what is this really? It's fundamentally interdisciplinary. So it's kind of interesting because computer science claims it, statistics claims it, and then they're the domain specialists, as computer scientists refer to them, which are the social scientists or the physical scientists. So it's basically a combination of anything that pertains to data. So statistics, visual analytics, machine learning, data mining, simulation, optimization, it all comes together. So again, if you have the time, this is now getting a little bit dated, but this is from Microsoft Research. It's a book, The Fourth Paradigm. You can find a free PDF on the internet. You don't actually have to buy this book. And then this is a statement in, I believe it was in Science, I forgot, where a group of people, this came out of an NSF workshop, where a group of people said, well, what is this computational social science about? And what is new about it, and what can we do with it that we couldn't do before? Because that's always the argument, you know. What's the big deal about big data? How can we now do things that we couldn't do before in terms of questions asked and types of analyses? Then this is the Venn diagram I referred to last time, the data science Venn diagram. And some people refer to the people in the middle as the unicorns. You may have heard this in those of you in the computational social science masters. That point was made in the orientation. So it's the same thing again. It's all kinds of statistical computing techniques. And one very interesting aspect is that in statistics, one never used to talk about where the data came from and what you had to do before you could actually do your analysis. But operationally, that turns out to be huge. I mean, in the literature, it varies from 60 to 80% of the work is cleaning your data, getting your data ready for analysis. Highly labor intensive, very inefficient. One of the main research agendas right now in this whole arena is how can we make this more automatic, right? So you don't have to go through your data line by line and find out which values are weird, right? So you see where we come from. We have the computer sciencey part. We have the math and the statistics. Traditionally, we have the social sciences, so to speak, substantive experience. And the whole point is that nobody can do it by themselves. Okay, that's why you see in the data science world, the typical mode of operating is the team. It's not the individual. These are teams consisting of computer scientists, statisticians, physicists, sociologists, you name it. But the whole point is that everybody brings something to the table, and this person in the middle actually doesn't really exist yet. It's really more of a concept of how do you bring these different perspectives together and help solve problems. And a big part of that is getting to the same vocabulary. As I mentioned last time, first time you see the term machine learning, you may think to yourself, if you come from a traditional statistics training, I don't know what that is. Well, you do, because a lot of machine learning actually uses statistical concepts and statistical models, but they think of it in a slightly different way. So you have to, for example, learn that a variable is now called a feature, but it's still a variable, right? And whether your linear regression is a statistics thing or a machine learning thing, it's still a linear regression. Or your clustering, k-means, everybody, well, maybe not everybody, but k-means clustering in statistics or in machine learning is the same thing, right? So it's a lot of this is the vocabulary, is understanding each other. Here's some of my favorite books. As I mentioned last time, the one on the right doesn't exist yet, but you can read it on GitHub as it comes about. This is one of my favorite authors, Hadley Wickham, in the R world. He's the person behind RStudio, and they, as I mentioned, were recently purchased by Microsoft, and so stuff is happening. Things are coming out regularly, and if you look at it carefully, you see that it all has to do with how can we make that initial stage, the data munging, data wrangling, how can we make that more efficient? You know? So what is spatial data science then? Well, it's data science plus space, right? This is my take on things. And we integrate geocomputations, all this stuff, spatial statistics, spatial econometrics, exploratory spatial data analysis, visual spatial analytics, spatial data mining. Why do I stress this? Because in most of these methodologies, space is not explicitly taken into account. Okay. So a lot of data mining, you throw everything in there and the solution comes out. But where these phenomena are is not taken into account explicitly. And of course, my personal bias is that that matters. Of course, the burden is on me to demonstrate that it matters and where it matters. And as we already saw, it's not going to matter in every situation. The situations where location is very important because it stratifies the social space, because it creates economic disparities, and all these kinds of things. That's where it's important to take space into account, right? And that's what we're going to see. So it's a lot of work. It comes out of this to appear book. It's a workflow. It's not a one-shot thing. It are different steps, and typically these steps play off each other. You know, so you get your data into the system, you clean them up, and then you go around and around and around, right? You transform them, you model them, you visualize them, you find patterns, you say, well, where does this come from? Can I model the patterns? You run a model, you look at the residuals, and you keep going until you have some kind of conclusion. And then a part that is often forgotten is you have to translate this to the outside world. And you have to, unless you stay in your bubble, then you don't have to translate anything. But the moment that you go out of your bubble and actually deal with policymakers, deal with a city council or a planning council, you have to translate what you're doing. And that's very difficult and typically not taught. You know, so if the class were smaller, I would make you make presentations, but I'm not going to even think about it with this kind of group. So what's involved? A lot of different things. Data manipulation, integration, exploration, visualization. The bottom line here is not one size fits all. Lots of different software tools. And so it's really important, and this is something you learn as you do, that you get a good sense of the landscape of the tools and that you figure out which tools are appropriate for which things. And that's one of the things we're going to do in the lab, is we're going to look at different types of tools, and you'll see how we can apply them. Let me skip the example because I'm running out of time, and I could talk about this in the lab, but this just basically tells you to do this particular analysis. We did lots of different things. We used Python, we used R, we used PostGIS, we used GeoDa, you know, and then the end result is a nice little map. We started with 6 million data points. So that's, now this stuff gets a little more technical. It may be, how do you connect the type of spatial data to the type of analysis that you can do? So in the GIS world, this is called the spatial data structure. And basically, for you, the main concept is that you know that everything somehow has to be translated into a geometry. Everything. If it's a location of a vehicle crash or an abandoned vehicle, which is what we're going to use in the lab, that becomes a point, right? If that location is on a particular street, that becomes a point on a network, right? If that location is in a given census tract, we aggregate it up, and then we deal with the census tract as an area, as a polygon. So these are the geometric fundamentals. That's what GIS is all about. I won't dwell on this, but there are these kind of data structures, data models that say how these things all work together. But let's think about this in a second in terms of analysis. So points. The location can be a random event. So crimes, accidents, locations of grocery stores, think of them as random events. Surfaces. Surfaces, air quality surface, noise surface, the array of things will have measurement on noise, and then you're going to try to interpolate that to get a measure for locations that weren't measured, right? Obviously you only have 500 sensors. What can you say about the locations where there is no sensor, right? That's spatial interpolation. Aggregate data, we call them lattice data. It's an unfortunate term, but that's what it is. Aerial units, census tracts, counties, countries, and then networks, right? Including social networks. A lot of the technology that we use in spatial analysis translates directly to social network analysis. Space-time, I just want you to know about this. We won't actually do this kind of analysis, but there's two different ways of thinking about this. One is the fixed container, and the other one is the variable. So the fixed container is when you have the same spatial unit and you follow it over time. For example, your sensors. The array of things, they're fixed, they don't change, they don't move, and you make measurements over time. This is called time and space in the literature. And then the opposite is where you have your Twitter person. There's a couple of, thousand of really crazy Twitter people who tweet all the time, and so you follow them. And you know exactly where they are at every point in the day, and so that's a moving object. There's some really interesting applications, buses with GPSs, Uber Analytics, they know exactly where you go from and where you go to. The cell phone call data are an example. Also in biology, animal tracking. So my sister is a biologist and she works with birds, and she's in Belgium. So they put these little trackers on the birds and they migrate back and forth to Africa. And then when they catch them again, they have the exact trajectory of where these birds went, where they stopped, how long they stopped there. How do you make sense of that statistically? This is not your textbook statistics. You really have to think about this. So these are the kinds of things we do with space-time data. And so then the different data types result in different types of analysis. For example, are traffic accidents randomly in space, or are they somehow clustered? This will be point pattern analysis. Given sensor measurements on air quality, what is the surface for the region? In other words, what is the air quality for the locations that are not in your sensor, right? Where are hotspots of mortgage foreclosure? This is not a random phenomenon. This is systematically organized. That's cluster detection. And for example, how are house prices affected by unobserved neighborhood effects? That's in spatial regression, which we won't do, but I still want you to think about this. And so then statistically, question is, are the data sampled, or do you have everything there is? For example, all the census tracts in the city. That's a population, or is it? We'll talk about that. Are the units discrete? So discrete units, census tracts, sensors, or is it a surface? And are they given census tracts, or are they themselves random? The locations of the accidents, for example, the locations of the crimes are a random spatial process. That's the theoretical term. So these are all different dimensions that come into play when you think about spatial data that don't necessarily come into play in regular analysis. I will skip the examples because you can look at them yourselves. They're just some pretty maps, the kinds of things we're going to do in the class. But now the pitfalls. There are 3 pitfalls, right? And these are terms that you will see over and over. And you may already be familiar with some of them. First one is ecological fallacy. What is ecological fallacy about? In a nutshell, you can't say anything about individual behavior if you deal with aggregate units of observation, right? So you're looking at crime and you use county crime data from the FBI. You can say something that the county crime level is associated with the unemployment rate in the county, but you can't say that unemployed people will commit more crimes. That is an example of an ecological fallacy. So as long, there's nothing wrong with this, right, with aggregate analysis, as long as you keep the limitations in mind, as long as you don't oversell it. When you do aggregate analysis, you can draw conclusions about aggregate units, but you cannot draw conclusions about individual behavior. In other words, you cannot draw conclusions at a spatial scale below the one you measure. So if you do census blocks, census tracts, you cannot say anything about census blocks. The other way works. If you start at the individual level, you can aggregate up any way you want, and it remains relevant. One way to deal with this with multiple levels, which we won't actually do in this course, is multi-level modeling. But multi-level modeling as such is not spatial analysis. This is a common misnomer where you see in the literature, I deal with spatial effects by doing multi-level modeling. Well, you don't quite deal with the spatial effects. Second buzzword, modifiable areal unit problem. Again, it has to do with scale. There's a famous paper, 1 million spatial autocorrelation coefficients, and it was an analysis of voting behavior in Iowa. And the author, Stan Openshaw, measured spatial autocorrelation starting with the electoral wards and slowly building up to higher and higher level of aggregation. And what he found is that the spatial autocorrelation changed magnitude and changed sign. Now, per se, there's nothing wrong with that. The information will change as you change the scale of analysis. The question is, you have to really know at which level you're working. And again, this has to do indirectly also with the ecological fallacy. The basic concept here, and we'll talk about this later in more detail, is spatial heterogeneity. Is that different processes work at different scales or at different locations. And just to illustrate this, in space it's a little more complicated than simply aggregation. You have both a scaling issue and what is called a zoning issue. So the scaling issue, let's say we start with A, B, you have smaller units. The zoning problem is that you have the same number of units, but the boundaries are different. And so that is in the literature referred to as MAUP, modifiable areal unit problem. It is one of the many instances where you have to worry about scale. And I'll say this many times, in spatial analysis, scale is critical, right? And so then the final one is the change of support problem. This is a little bit more technical. It is the case when variables are measured at different scales. So let's say you have some individual level data, but you also have census tract data or zip code data, which is really bad, but we'll talk about that later. And this, you can have one situation where they're actually nicely nested, like, counties into a state. So the state is the sum of all the counties, so there's a nice hierarchical situation. But also, in practice, very often, you don't have that. The example I already gave is school districts and census areas. They typically do not match. And then the solutions are aggregating up to a common scale, but if that doesn't work, the only way to deal with is what is called imputation, is making data up. And the only way you can make data up in a rigorous fashion is by taking a Bayesian perspective. And we won't go there, it's a little too complicated. We won't go there in this class, I should say, but that is kind of the array of the types of problems. So basically what I try to do here is get you aware of where I'm coming from, what is the spatial analysis, what is the data science part of it, what are the kinds of data situations we'll consider. So we'll consider what we call aerial data, which is the most common analysis. But that's aggregate analysis, so it gets us into potentially ecological fallacy issues. We'll deal with point data, which are individual data, but there's a selection problem here because these point data are events. We don't have the non-events. So we have the location of the car crash, but we don't have the location of the car crash that was avoided. And so that creates other statistical problems. And then when we have our sensors, we have fixed measurement points, but then we have an interpolation problem. How do we make data for the locations where we don't actually observe the data? And how do we know how reliable that data is? How can we interpret the precision of that data and the error structure and so on? So that's where I'm going to keep it. As I mentioned to you, I'm still gauging the speed here. I think I went a little bit over time. I did, didn't I? No? I go to 250. Oh, why did I think I went to 220? Okay, well. Okay, well, I'm going back then. I'll talk about the examples since I now, I got that totally wrong. I'm sorry. So no wonder nobody was scrambling to leave, you know. So let me just spend a few minutes and then we can have some questions. And I'll go slower next time. Okay, so this digital neighborhood thing, we looked at Twitter messages and Foursquare location data. So we have one particular week, and we ended up looking at 500, close to 600,000 data points. But those data points came actually from more than 5 million messages. So you start, I don't know if anybody has worked with Twitter data, but they come in a JSON file. You know, JSON is a particular format that we converted to simple comma separated, you know, so you have to have a script to write this either in Python or in R. And these messages were in almost 6,000 different files. So you're not going to do this by hand, right? This is not going to work. So then we basically had to select those messages that did have the geographical information, and typically about 5 or 6% of them do. We had what you call the fire hose, which is everything, not the little sample that Twitter gives you. So more than 20 gigabytes of memory. So again, I mean, is this big data? Not for us, because we have big computers, but if you have, 2 gigabytes on your laptop, it's not going to work. So then we put this in a spatial database, so we can do all the different spatial queries, and so that requires, in our case, we use PostGIS. We aggregated the points up to the aerial units, in this case, block groups. This is something you're going to be doing in the lab, and then you can do this in R. You're going to do it in R in the lab, or you can do it directly in the database in PostGIS, which is a spatially aware database, as opposed to, Postgres as is, which is not spatially aware. And then we run a local Moran, which is a technique that we're going to see later, and we visualize that using GeoDa, and so then out comes this pretty map, which is a measure of the clusters of high intensity use and low intensity use. So we use this to define so-called digital deserts. Think of them as like food deserts, where the use of the social media is underrepresented, and then versus digital hotspots, right? So that is an example of what I call spatial data science. What you notice in here is that there's a lot of prep before we actually get to the analysis. Now, the prep part, I would love to have a whole course just devoted to that, but unfortunately we'll have to limit it to just one lab. And as I said last time, every one of these lectures could be a whole quarter-long, even semester-long course in its own right. So we're going wide, we're not going wide, not going very deep. So what we'll do after the first lab is focus on the analysis, focus on the techniques. not dwell too much on the data prep. Okay, then let me move. So I gave this lecture at another place and it took me 90 minutes. That's why I was so paranoid that I would run out of time, and I had the clock completely off. So let me come back to this, and we have the different kind of data and the types of data research questions that we can ask. And so points, and since I have a little bit of time, let me dwell on this. Points can be incredibly confusing, because from a geometric point of view, a point is a point, right? You have x and y coordinates, that's it, right? From an analysis point of view, this point can be different things. For example, it can be the location of a crime, of a shooting. In that context, the point is a random variable. The location of that point is random. And what we're trying to understand is, what is the spatial process underlying the locations of these points? So it's not deterministic in that the point could have also happened somewhere else. But what is the chance that a shooting happens in a particular location? So you may see this sometimes, these risk surfaces, right? So what is the chance of getting into a car crash? Where does that come from? That comes from looking at the events and then trying to figure out what is the spatial systematic process that yields the events, then mapping that out. It's now several years ago, I was involved in a study that was looking at creating risk surfaces for, what do they call them? These devices, so basically self-made bombs in Iraq, you know, so IEDs, yeah. So what we had was a map where these IEDs had exploded, and so from that you try to come up with a risk surface that then allows you to allocate resources in function of the risk. You know, you may have heard the term predictive analytics. It's a really big deal in crime and policing these days. That's what it's all about. Predictive analytics is trying to figure out what is the chance that something is going to happen in a particular location. Obviously, this is not uniform. Some locations are going to be more prone to have stuff happen than other locations. And how do you then build that into your resource allocation, right? This is an example of a data set that we use a lot for GeoDa and some of the other software that we develop. These are car thefts in San Francisco in a particular 6-month period. This is for real, right? So if you look at the map of San Francisco, you're probably going to say, you know, I do not want to park my car there. This is a heat map. This is one of the tools. You may be familiar with this because everybody's doing this now, but it's actually a technique to measure a probability surface. So where the colors are more red, white is the hottest, that's the highest probability of getting your car stolen, and where it's, you know, basically invisible, there's negligible. This is all well and good, but what is a very important factor that I haven't brought up here, when you think about it for a second? Exactly. So this only gives you the density of the vehicle thefts, but it doesn't actually give you a measure of what is the probability that your car would be stolen, because there could just be that there are many more cars there. And in fact, it could be that the chance of getting your car stolen is uniform, meaning the same everywhere, but there's just more cars stolen there because there are more cars to steal, right? So that is something that we'll have to take into account in the analysis that we do. We'll have to make sure that before we say, oh, this is a hot spot, this is elevated risk. Well, these are car thefts. Translate this into Ebola outbreaks, right? Or anything else, gang shootings. is this really a hotspot? Is this really an elevated risk location? Or is this just because of the underlying population, right? And that's a very important thing we'll have to keep in mind. Okay, so then that's an example of point pattern analysis, which we'll do towards the end in a class. So this is another study I was involved in looking at air quality in Los Angeles. Now, how many people are from California? Okay. So how do you feel about a single number for the air quality in Los Angeles? I mean, if you've been in Los Angeles, the air quality is not the same everywhere, right? So this is one of my pet peeves. A lot of these analyses, they give you a single number, but in fact, there's a lot of spatial heterogeneity underlying. Air quality is an example, poverty is an example. You know, you name it, just about everything you study, when you look at cities or larger geographical areas, summarizing them by a single number is a huge simplification because it ignores the underlying heterogeneity. The example I often give is, you know, you have maybe it doesn't happen so much with census tracts, but it happens a lot with zip code zones. Let's say an imaginary zip code with a rail track in the middle, and you have the right side of the trail and the wrong side of the right side of the track and the wrong side of the track. And then you average these two. So let's say one is a very high income area, one is a very low income area. The average, or even the median, is going to be something that doesn't exist in that zip code zone because it's either high or low. The middle doesn't exist, and the middle is what you get as a result of spatial aggregation. So that's something we have to be, or at least I try to make you very aware of these kinds of phenomena. So in LA, the air quality is very uneven. Some parts of LA, like, you know, Orange County, very nice. If you move out Riverside, San Bernardino, better wear a mask, you know, or shut off the vents in your car. So we were interested in finding out how air quality might affect house prices. And so how do you do that? Well, the little points on the map are all the individual house sales that we had, and the triangles are the 33 air quality monitoring stations. So obviously we had something like 300,000 house sales. We don't have 300,000 monitoring stations. So we need to come up with the air quality for 300,000 of these house locations from the measurements at these 33 stations. And that's what geostatistics does for you. We'll see how that works. And out of this comes a so-called interpolated map, which is based on a technique called creaking. And so this is an instance where the points are not random, but the points are actual measurement stations. They're given, they're fixed. And then, but to the map, to the GIS, they're just points. So you're the one who has to know whether this point is a random event or whether this point is a measurement station. There's even a more extreme example. Let's say you work with counties, but you don't actually have a GIS, you don't have a map of the counties, but you have the county seat with latitude and longitude, with the coordinates. So then the points, in that case, are actually not even actually points. They represent the area. And so you could treat them as points, and the software doesn't know any different, right? The software doesn't know whether these county seats are car crashes or are sensors measuring air quality. To the software, they're just points. It's up to you to know what these points represent and what kind of analysis you can do with that. So the last example is this is Franklin County. That's where Columbus, Ohio is. And these are foreclosure rates in 2007, just kind of going up to the crisis. And the question is this spatially random or is this somehow patterned? Okay, so then what we do, and we'll see this, there's many different kind of hotspot cluster detection techniques. One of them is based on local spatial autocorrelation, and you get these kind of maps. And then in the exploratory process that we carry out, you use these kind of maps with other maps and with graphs of the data to try to figure out, are there any kind of systematic patterns or associations between these hotspots and particular other variables. And then at the end of the day, you put that in a regression model and so on. We won't go that far in this class, but I should be pretty good at squeezing my semester into a quarter at the rate that I'm going, you know. But anyway, this is one of the important tools in exploratory data analysis. So since we have a little bit of time, any questions?
Do you have like car model information for the San Francisco?
Car model?
Yeah, like model that was stolen.
I think possibly in the original data that could be there. I don't think it's in our set, but the abandoned vehicle data set that you're going to be working with in the lab has the models, and that it actually has everything. But there's a lot of missing data.